This video is about schematic diagrams. It corresponds to section 7.10.3 of the Applied Analog Electronics textbook. In this video, I'm just going to talk about schematic diagrams and not show you how to create them with a tool. That will come as a separate video. Okay, what is a schematic diagram? Well, this backdrop that I've had behind me in all these videos, that is a schematic diagram. And the purpose of a schematic diagram is to expand on the block diagram. You remember that in the block diagram we had blocks that had functions and we had connections that were signals of some sort. And each block took in some inputs, produced some outputs, and everything there was kind of generic in that we didn't say whether the signals were single wire, 2 wires, 100 wires. It could be anything. It was just drawn as a line to say there's an input coming in here, something carrying the information. The schematic diagram is different in that the lines in our pictures now are going to correspond to nodes in the circuit. They're going to be things that are all at the same voltage. Basically, think of them as wires. So we have got to expand on the block diagram. If it had a signaling convention that required 2 wires for the signal, that was a single line in the block diagram, but it'll be 2 different signals, 2 different nodes on the schematic. So we're going to have components that are physically realizable things like resistors and thermistors and amplifiers, and wires connecting them. Let's take a look at what some of the symbols are that we can use for these components. Okay, these are most of the symbols that we'll end up using in this course for schematic diagrams. The symbols here are the American symbols for a number of these things. There's a different set of conventions that European schematics use, and I have chosen deliberately to use the American conventions because the symbols are much more visually distinctive. The European ones seem to have been selected for ease of drawing on a pen plotter. And that's really not a very good criterion for picking symbols. These symbols are classic ones that were picked actually more for drawing by hand than for drawing on a pen plotter. But they're visually quite distinctive, much more so than the European ones. So we'll be using the American standards. Now, there's 2 different groups of things I have here. There are the components that are pretty much grouped there in the middle, and sort of scattered on the edges also, and they're the ports. Remember, the ports are what we use for the schematic to communicate with the outside world, the stuff outside this schematic. And that's not necessarily the outside world in the sense that you might think for a sensor system. It's the stuff that's outside this particular drawing. So if we have a schematic that corresponds to 1 block of our block diagram, well, the blocks it's connected to at the input and the output, those are outside. So we need to have ports to connect from the schematic for this block diagram to the schematics for other block diagrams. And that's what the symbols in the upper left corner here are used for. The generic port, which is just a little circle on the line, you connect wires up to that line, that just gives a name to any symbol, any wire in your system. And you can use that for any sort of generic connection. It's this wire here. Anything else that has that name, if you've got another one of these generic symbols with that name on it, it's connected together. And sometimes it's done for connections on the same schematic because it's just too hard to draw a line that runs all the way across the page. Things get too cluttered, and so you just say, oh, this is this, and on the other side of the paper you put another one, and they're implicitly connected together. They're also used for that same sort of connection which goes between pages of the schematic. But they're not used a lot for that purpose unless you have a bidirectional connection, because it's much more useful to your reader. And remember, schematics are intended for human reading. It's much more useful to your reader to indicate which direction information is flowing. So we usually use input and output ports. An input port on a schematic corresponds to an input on a block. It's something that's coming from a previous part of the system. It's information coming in on this signal. And outputs, similarly, are, well, this is what we're providing to some other block, passing it down to them. So inputs and outputs, though they have the same physical connectivity as each other and as generic ports, things with the same name are all connected together. They're more mnemonic in that they tell the reader of the schematic what it is that this connection is doing in the schematic. I'm supposed to be providing input here. I'm supposed to be providing an output out to something else here. That information is very useful in trying to figure out what the circuit does and debugging it when you're trying to figure out what it works. Incidentally, your schematics have to be drawn before you build anything. If somebody in the lab ever asks me for help in debugging their design, pretty much the first thing I'll tell them is, show me your schematic. Because debugging, which is a process of trying to figure out what's wrong with the system, a large part of it is trying to separate what your expectations of the system are from your observations. You have some discrepancy. It's supposed to do this, it's doing something else instead. And you want to figure out where in the process things have failed. And the schematic diagram encapsulates the design you were trying to build. And so one can then look at the schematic and say, this looks like it ought to work. And you can then look at the schematic compared to the thing you actually built and say, wait a minute, this schematic doesn't match what you built. Your implementation is wrong. Other times you look at the schematic and the implementation and say, those look like they match. Maybe there's something wrong in the design. It helps you kind of narrow in where the problem might be. So you need to have a clean schematic, all the components on it, all the component values, everything labeled, so that it's easy to compare with the implementation and not, oh, well, I changed a little bit here, but I didn't change the schematic. You didn't change the schematic? I can't help you. I've got to know what it is you were trying to build. And that's what the schematic captures. Okay, so what components are you going to be likely to be using in your designs? First designs are going to stick with just a very small number of components. The resistor, the thermistor. Notice that they have very similar symbols because they're both resistors of one sort. The thermistor, because it's temperature sensitive, has that little T next to it, and the circle around it to indicate that that's temperature sensitive resistor or thermistor is a single component. Some of the other things that you might be using, the function generator. Now, you're not going to build a function generator. That's a bench instrument, or for most of you, an Analog Discovery 2 capability. And so you don't always need to put that in your schematic. Sometimes you'll just say, I have an input port. The signal comes in here, and I'll hook up a function generator to the input so I can test what's going on. So if you're just doing something where a function generator might get hooked up for testing, but it's not really part of your design, then you don't necessarily have to put the function generator into your schematic. If you do decide to put it into your schematic, then function generator has two connections to it. Make sure they're both connected, because anything that's not connected on a schematic diagram indicates a problem. Either the schematic diagram was never finished because you've got this wire that's not connected to anything, or sometimes that there's something that's deliberately not connected. You have a component where it's got some control parameters, and if the control pins aren't connected to anything, it doesn't matter. It means some default value is used. Then you should put a little NC next to that connection on the schematic to indicate not connected, so that the reader knows this is a completed schematic. That wire that looks like it's just dangling, it's supposed to be just dangling. It's not connected to anything. Another thing about ports. There's a couple other ground symbols that you'll sometimes see in people's schematics down here at the bottom that we don't use. The chassis ground and the earth ground. Now the earth ground is very important if you're doing radio electronics or if you're doing power grid electronics, well, not even electronics, power grid electricity distribution, because the earth ground is what it sounds like. You take a big copper rod and pound it into the ground, and that is one of the nodes in your system. Important for radio electronics because radio propagation depends on there's a ground plane down there that interferes or is used in various ways in radio propagation. We're not dealing with that. The grounds we use are just arbitrary nodes in our system. They're isolated grounds, and we don't want them to be confused with earth ground because they're not the same thing. So we will not use the earth ground symbol. We will use that open triangle at the top there to indicate that we're using an isolated ground, something that is not connected to that earth ground that's out there. The chassis ground is kind of an obsolete symbol. That comes back from the days when vacuum tube systems were built on big aluminum objects. That was the chassis, and that chassis, because it was a conductive metal plate, was a node in the system. Sometimes it was connected to earth ground, sometimes not, but there was connections to chassis ground. We don't build on big aluminum plates or steel plates anymore. Most of our stuff is built on printed circuit boards. We do not have a chassis usually that we can connect to ground. So chassis ground is pretty much obsolete in modern electronics. So don't use the chassis ground symbol, don't use the earth ground symbol for this course. Just the isolated ground symbol, the generic ground symbol, that's the open triangle. Okay, that's probably all the essential stuff. Now, one more thing. The amplifier and amplifier with power that's up here above my head. Amplifiers always need power. By their very nature, you have to provide power to amplifiers. So why do we have an amplifier symbol without power connections to it? Well, it turns out that in a lot of systems, we only have one power supply, and everything that needs power is connected to that same power supply. And running wires all over the place for that would be a pain. And even using the power symbol and the ground symbol for our power connections clutters the diagram a little bit. And so if all the amplifiers and all the components that need power are connected to the same power, some people use the convention of just omitting the power connections and not showing them. And that's fine for experienced designers. I'm going to recommend that for beginning designers, you use the symbols which have the power connection, because I would say 20 to 30% of the errors that I see in student designs are they forgot to connect power to the amplifier. It's the first question that any call center asks if you have problems with your computer. Is it plugged in? And forgetting to connect power is a very easy thing to do. And so I'm going to recommend that your schematic diagrams, you always use the amplifier with power symbol rather than the amplifier symbol that doesn't have power connections. And that's probably enough generically about schematics. Quick review. Lines on a schematic are wires. Components have these fancy symbols, and you have to pick the right symbol for them. Any connection that goes outside the schematic has to have a named port. Input ports, output ports if they're carrying signals, power and ground ports if they're just constant inputs, generic if it's some sort of connection that's not easily classified as an input, output, power, or ground. And if you've got multiple schematics in your system, anything with the same name, any port that has the same name, is the same wire. So if you've got something called V-in, something else called V-out, the V-out can only be connected to something else called V-out. The V-in can only be connected to something else called V-in. They're not local names to just this particular block. They are global names. And so be very careful to name everything, every port uniquely. If two things are supposed to be connected together, give them the same name. An input port and an output port with the same name means that that output is connected to that input. Okay. Always produce a clean schematic, one that's actually one you can show to somebody like me before you start building your circuit. Because if you don't have a clean version of this is my design, then it's almost impossible to debug the design.